Okay, let's get going with the lecture. Today, lecture is entitled Risk and Return. Now, you notice I didn't put any pictures here, and there's a good reason for that. I wanted to, just because I always do. And this time I thought that these words are appeal to the fascinations more than enough to stand by themselves. Okay, so both risk and return are topics that I think are of paramount interest in economics, especially in finance. If there's anything it is about, it is those two things, risk and return. So the idea is, of course, that there is only one way, or only two ways to make money. Either you got to work for your money, or you got to take risk. Working is no good, but taking risk is probably worse. That's why it gets paid more. But anyway, that is besides the point. That's not what the lecture is about. What we want to do is see if we can approach this subject from the subject that we've been breaking open, which is the Laplace transform and the S-domain. Now, I'm going to give not a comprehensive account of what risk is. What we'll be talking about is what is usually called and referred to as interest rate risk in finance. So if you hold some kind of security, then the value of that security may change when interest rates change. And because then you will have to discount it at some other rate, and all of a sudden it's worth quite a bit less. So you see this very strongly, this effect in the stock market, when the Federal Reserve changes interest rates, the stock market moves immediately. There are certain investors who think that that's basically the only factor driving the stock market right now. And whole books are written about it, about don't fight the Fed, which is the slogan. But it's not just securities, it's other capital goods like housing. Housing is very much tied to how you're going to discount the loan that you get to buy the house. You know, somebody's nodding here, and his name is Joris Lardinois, and he knows this as no other in this group because he studies the housing market and real estate, and he can confirm that that's the basic driver of housing prices. And you would think it's the bricks or the mortar or maybe the window panes, but really it's
drivers, the interest rate and the incomes.
Yeah, income.
What can you pay and how expensive is it to pay?
So the rate of return on your work and the rate of return on your, you know, huh? So that's it. That's the two drivers. You know, the amateur, he thinks, or the non-economic engineer, he thinks it's actually the bricks or something like that. But it isn't. Those are the drivers, okay? So it's very, very important. And the same goes for return, and they kind of go hand in hand. The idea is that you won't take risk if somebody doesn't offer you a return for that, okay? And you don't get a return without taking some risk. So these are the topics we'll start with. Up till the break, I want to do risk, and after the break, I'm going to do return. Now, there's a curious thing here that I'm going to do risk totally in the Laplace domain, and you will be able to follow me because you'll know you'll be able to do this with the Laplace transform, and all these things will make sense. However, there's really no good engineering analog to an application of the same analysis. I looked all around. I found something in acoustics of guys doing this, but very sparse. It's just something that we could do, but we just kind of never do. All right, now if you have a different opinion, I'd love to hear from you about this. All right. The interesting thing is on the return part, what I want to do after break is precisely the opposite. We know enormous amounts about this, and we deal with it all the time. And but yet in economics, nobody really knows how how to comprehensively deal with it. They have some very primitive tools, and then they throw their hands in the air and just say it's a difficult problem and nobody can really solve it, okay? So this is an interesting kind of setup that we find more often, you know, that something that's really hard or not used in one domain gets very much used in the other, For instance, we're still here, don't forget, only dealing with the real part of the Laplace transform, you know? Now, very little that gets used in engineering design. I know they're over-damped systems, but who worries about them very much, you know? I mean, they're always stable anyway, so then it seems that everybody is kind of, you know, kind of fizzles out by then and says, well, that can't be interesting, okay? Huh? And then especially when you have growth, they'll just declare this is unstable and therefore should not be considered, okay? So you see, this is this kind of a weird thing. For us, everything is interesting, okay? So let's start off with the risk part of the show. And let me talk a little bit of, this is a bit of a busy slide, but I want to give you a sort of a quick intro on what this is all about. And the words that are used in finance, and I'm going to talk especially about bonds. So, you know, a mortgage is like a bond, and all these things, a security can be viewed like a bond, you know, where the dividends are the coupons. But this business has been developed most thoroughly applied to bonds. So I'm going to take that, but keep in mind that this can apply to any financial instruments and doesn't have to apply to effort or forces, you know. We can also look at quantities and stuff and take the Laplace transform, and all of these things will have a different interpretation. But just to fix the ideas, we'll take these bonds because they're quite sophisticated, these types, okay? And they'll talk about things like risk exposure and then immunization and gap management. Now, Britt and Emil, and especially Britt, in this case, they are working at Rabobank, and gap management is a very important issue there. So what happens, a bank like Rabobank, they have their depositors who they give them money, who they have to pay interest. And they have their customers, which are the people who they lend money to. Well, those are the vendors, sorry, hey? And who pay them interest, okay? Now, one of the problems they face is that these depositors, they can ask their money back at any time because they have these checking accounts. And the lenders, they can't get the money from the lenders at any time because they're committed to have an investment for so many years, okay? So what can happen to the bank is, although everything balances on the balance sheet, they have as much deposits as they have assets, that all of a sudden might even be a run on the bank. People want to get their deposits, but they can't get the money from the loans they have outstanding, okay? And this creates what's called a gap in duration. So duration refers to the time it takes to get your money back. Okay, so the duration is very short on the liability side, that's where the depositors are, and it's very long typically on the asset side where the lenders are, you know. Ones are, you can get any day, you can get your money, right? And the others, you know, you gotta wait for years maybe to get your money, all right? So there's a gap, a difference in what is called the duration. So this duration, that's some kind of measure for when you can get your money back. That is a measure of the risk that the bank has, you see?
The other side of the coin of liquidity?
No. No, liquidity we'll get to after the break when we talk about returns, right? There's no coin here, there are no two sides. There are just one lecture with before the break and after the break, all right? So now we're just talking about this. Let's throw everything away, you know? You have a single, say, cash flow, right? That's a want, or what we would call an economic force, all right? And you take the Laplace transform of that, you get the value of that, you know? Now suppose that this is a single payment at some time tau in the future, right? And then it has a certain duration. And what would that be? That's exactly that period, right? You would think intuitively. So if another loan has a duration of 1 day, which is the deposit, and the other like a year, you're going to have some gap between these two, okay? Now the problem is that in general, if you have a loan, it's not just when they pay it back, the principal, but you also get in the meantime interest payments, okay? So this loan is already generating cash flow before the principal is due, all right? So the effective maturity or the duration should be shorter because you already got some money in the meantime. You know, the first year you may get some interest, or the first half year, and then. So rather than 10 years, it should be a little bit shorter, right, to account for all the payments you got before, all right? Now, the concept of duration is exactly what that is supposed to measure, all right? Now, this has been defined by a guy called Macaulay, all right? And what he did was he said, well, what I want to do is see when the payment comes, okay, at some time in time. So here it is. Here's a payment, here's a payment, here's a payment, right? Now, this coming after a half a year, this is a year, this is 1.5 years, you know, 18 months. So what I want to do is I want to take the present value of that. So I want to discount that to the future, right, to the present, sorry. And then I'm multiplying by the time it takes to get there. So I'm kind of looking at the leverage. That's what this guy, this is from Wikipedia. This is what he means to say. Like this one has more and this one has less, and this is how he does it, right? Okay? So you multiply the payment by the time and you look at the present value. That's all this is saying, right? You do that for all payments, so you sum over this dt, right, f dt, and then you want to look over the present value of the whole thing, you want to divide by it, okay? And then you get something in time, and that is called the Macaulay duration, all right? So it's a complicated formula. You may ask yourself why you do this, but you can kind of feel that that's not a bad idea, right? So if you get a single payment at time t, then you just discount that, and out of this, and then you divide again by the value discounted, so you just get the maturity, right? When you get the payment, okay? But don't worry, you pretty hear too much about this formula. If you look at this from the eye of the engineer with the Laplace transform, you go, well, seriously, I know what this is, right? This thing is just the Laplace transform is the derivative of the Laplace transform. Because you go to your table, you know that if you look at the Laplace transform of t times some function, that is equal to the derivative of the Laplace transform. All right, so we looked at that. You should know this. Okay? So I can write this thing just like that. And there we are, and this is what they would call modified duration. Now they don't know this. So they will say we have two definitions of duration, and in certain situations they're equal and certain they're not. When you look at what they do, you'll see that when they're not equal, they're just not accounting for this integral correctly, and they don't, not doing that because, or they're not discounting it exponentially, one a little bit more than the other, but they're equal. Okay, set up this way. So this is the first thing you see from our Laplace transform, this notion of duration that takes these types, it takes them at least a year, 2 years, I don't know, in bond investing to understand this, should take you just a few seconds as an engineer, okay? That doesn't mean you can work with it, but mathematically you can see very quickly what this is, all right? Then sometimes they won't divide by the present value, and that they call dollar duration or DV01, especially in the United States. I have some other names for it. This is the dollar value of a basis point. The 0.1 is a basis point, as a hundredth of a percent, and this is the dollar value of a basis point. This is just some terminology, okay? Okay? Whatever. If you look it up at Wikipedia or Investopedia or whoever, you know, that's what they'll say, all right? Okay? And then they'll say, well, okay, but, you know, I'll have this duration, but what if interest rates change, then I'll have a new duration I'll have to calculate because this thing is done at S, right, this derivative. So what can happen is I look at the duration, so I know how risky the bond is, but now the interest rate or the discount rate has changed, and at a different point I have to recalculate what the duration is. And then you can look whether duration is increasing or decreasing, and that's what they call convexity, okay? And very sophisticated types will look at this, okay? So they will want to check whether their bond has convexity, whether things are getting worse or are getting better, okay? All right? So you can see that this duration is a measure of risk, right? The longer the duration, the more risk you have, because the longer it's going to take until you get paid back on your loan. All right? So here's another graphic that they'll have when they explain convexity. So here they'll look at the bond price. So I would call this the value, right? But they call it the price, that's fine. This is the yield. I would call it the discount rate, but some people call it the yield. These guys call it a rate. There's also a yield. This is because of bonds, but usually they'll call it a rate or interest rate. You know, it all varies. I guess yield is a typical bond terminology. When you think of a bond as sort of a crop that you have, and I look at your crop yields like an agricultural thing, you know?
The bond yield is a special kind of discount rate, where discount rate is a general term applicable to everything.
Yeah, it is specific to bonds, you know, because let me after the break I'll say why I like it and why I don't like it, what I wanna change, you know, to make this. But just say yield, discount rate, interest rate. Some people talk about changes in interest rate. You know, Wikipedia will talk about the changes in the interest rate. These guys will talk about changes in yields, you know. So when you take this derivative, so, you know, they all use something different depending on their application, right? But it's just the S variable that we're changing, okay? So if you look at that price that has some kind of graph, right? You know, here is V of S and here's S. I mean, this is just the Laplace transform. So it's just going to have some graph. You know, this is real, right? Huh? And this is not a log scale, so that might not be a Bode plot, but some kind of graph like this, okay? And then you can see then what duration does. It's just the first derivative. You see, you know, how it approximately behaves here. And then this convexity, they'll see it as the curve, the second order derivative, the second order change, you know, and then you'll see that they'll see this is overestimate the price decrease. Here they underestimate it. You'll see they'll have to apply another correction for big increases in yield here, okay? It's a mess, all right? But what I want to do with this slide is not make you understand this full business. I mean, it's easy to see this from the internet, but have a feeling for what they're doing, okay, and how they try to deal with this gap management, immunization, and how they quantify these interest rate risks, okay? So they use this concept like duration. It's not adequate for big changes in S, so they'll look at convexity here, right? Huh? And then in that way, they're going to try to get a handle on what's going on here and how risky it is and how they have to price it. The more risk it is, the higher the price, okay? So the higher the duration of the bond, the higher the price goes up. That's sometimes given by a curve called the yield curve, and that's the idea, all right? So we're measuring risk using these risk factors. So these are two risk factors, all right? So you can see this all has an easy explanation in the Laplace domain. I mean, you just go like this. What's the story behind this? Okay, what's the general story behind this? How we would be able to look at what's going on here rather than just calculate some stuff. And that's what I want to talk about until the break. Okay. So let's go to the next slide. And here I say, all right, let's look at this type of risk now from an engineer's perspective. What's going on here? Now, you look, they have the first derivative, they have the second derivative, and what they're doing is they're trying to find out how this value will change with small changes in the discount rate, okay? Now, if you want to look, analytically speaking, right? So you've done your first course and your second course in math, and you want to look at how a function behaves for approximate the behavior of function for changes in the variable, right? So you have a sine curve, or what would you do? Would you take a Laplace transform? Would you take a Fourier transform? Will you do this? No. Right? You will do a Taylor series expansion around the point at which you're interested and you're looking at the changes, right? So you're at some point, and then you say, well, I'm going to change this a little, and then I'm going to see, first I'll do a first order change, so that means all quadratic terms will be 0, then a second order change and a third order, and then I add orders as my change gets bigger, and then I know by the Taylor series theorem that this thing would converge, you know, if I have an analytic function, and I can find the function to any degree of precision, no matter how big I make the variation. That's the idea of the Taylor series. So who doesn't know that? Right? Who doesn't recognize that, I should say? Nobody knew it, but you recognize this. That's the idea behind the Taylor series, right? So now let's look at this function, the value, right, as I change the discount rate or the yield or whatever I call it from some point, say R, you know, that I am right now, right? So this point R could be some prevailing rate, or maybe the risk-free rate. That's nice that it's called R, or maybe it's desired rate, or I don't know what it is, but at some point that you set, okay, the current rate. Huh? Is that what you said?
No, but
yeah. Clear, yeah? And then you go and you change it a little bit. So the change would then be, or the movement, they say, call it the movement in interest rate, will be where you are minus, no, that where you are going to end up minus where you were. All right? Huh? And then in order to calculate S, what I would do in the Taylor series, I'll first say, okay, my value where I'm going to be now is where the value where I was at R, plus the first derivative about times the change, plus a half times the second derivative times that change, and you go on like this to 1 over n factorial, I think, you know, V, something like that, right? I believe that's the Taylor's theorem. Or I got this factorial right and it isn't in there. But yeah, I think it is, right? This is it. Okay? And now we can recognize this term as being the dollar duration. You know, that's just the definition. And this term we can recognize as the dollar convexity, and we could potentially add all kinds of other terms. Okay? So we took their terms now and set them in a little better context, you know? So we can express the value where what will happen to us, you know, compared to where we are in terms of a first order effect that's equal to that. I believe this was a minus sign, right? Because it was minus that. Huh? I defined this to be the negative, and this is the positive. That's how they do it. Huh? It's right for once. And then plus the first order, so we see that the duration is the first order effect, measures the first order effect in the value. Huh? The convexity, the second order effect, and we can come up with all kinds of things, skewness, whatever we feel like, right? But let's just stop here, okay? Well, that's satisfying. So all we did here was look at our Laplace transform and did a Taylor series expansion of it to approximate it. Now I see guys do this a little bit. They have some complicated system and they get sick of it. So they want to approximate it with the first order system, and then they do these kind of tricks. Now typically they don't take a Taylor transform, they start searching for some dominant poles and plop those in there. So it's not quite a Taylor thing, because they're not looking for small changes in the frequency. But I bet you if they were, they could approximate a complicated transfer function or system for a Laplace transform using this formula, right? Huh? I mean, you can imagine that. Have you seen them, Kuhn, or anybody do Taylor's formula for small changes in the frequency?
I don't know.
Yeah, I don't know either. I bet you somebody must do it because it's too obvious, but anyway, that's what I meant. Like, it's so obvious what they do, and now, like, well, how do we do it? And then with real values for the S parameter, that's even more like, why would we ever do that? But there's nothing wrong with it, huh? So you see, this is a neat result because these kind of things, durations are really easy to determine. You just start taking derivatives here, It's just very, very simple, and you can easily calculate all this stuff. Now, what they will do is not look at duration, dollar duration, but look at duration. So the trick that we can do is look at this thing, and I call it R for risk, but really it's some sort of percentage loss, right? So you look at where you were minus where you're going to be, and then divide that by the value of where you were, right? And you look at that percentage, that will be the loss that you made on this investment, okay? And if it's positive, of course, it's a profit, So this thing here is some metric that you could use. Now, how would you do that? Well, you would pull this over to that side. You will put a minus sign. Let me do it over here. Pull this over here. Put a minus sign in front of everything, right? You just start plugging this in, and what do you get? You get this. So here I just plugged it all in with by dividing the Taylor series by this number and putting a minus sign and subtracting, and then you will see that this kind of loss function or risk function doesn't have a zeroth order term, of course not, because we subtracted it out. It's just a change, right? It just measures a loss, a percentage loss, and it has a first order term that's proportional to the change in the discount rate, and it has a second order term here that's proportional to the convexity, okay? Well, this is a very neat way of encapsulating your losses and in terms of duration and convexity. So for us, it's almost more worthwhile to work with this function and then later kind of calculate whatever these things are. All right? Okay? Well, this is a generalized tool, and let's go through some examples to get a flavor of what that thing is doing. But the idea is you can plug absolutely anything in here, right? That doesn't have to be one signal. That can be the difference between two things, like an investment and a return. And you just look at that difference and you see what the duration is. And then you're doing gap management, So you look at the value of your deposits, you subtract the value of your assets, your loans, and then you look at the duration of that difference, And if you then divide by some current rate that you are, then you can easily see what your risk is, okay? So you can go nuts with these things, okay? But that's not what I want to do in this lecture. I want to take a few of the Laplace transform we had and just start calculating them and see that it all lines up with what they find and give us a little bit of a feel for that. Okay? So we actually did achieve quite a bit here. And let's start with the simplest of all, which is a spot payment, right? So you know what it is, right? Here's time. Here is your want, hey, your cash flow, and I'm just giving you some money right now. Now, what's the risk associated with that flow? I mean, you don't have to think at all. Zero, of course. Huh? There's no possibility of default or anything, right? Or, you know, it's all happening right now, okay? So the duration is zero, the convexity is zero, all the terms are zero, right? The whole thing has got zero risk, okay? Now let's just plug that in and see how that comes out, right? So the present value is 1, right? So as a function of s, it is 1, right? So what does the Taylor series look like? Well, you got a 1 there, right? And all the other derivatives are all 0, right? So you're just going to add a bunch of zeros. So the duration is 0. That's the first derivative. You don't know. So what's the risk? You subtract 1 from, you know, wherever you were. That's also going to be 1. You know, suppose this is r, right? Also 1, just 0.
Can you show the equation for r again?
Here you go. Huh? So really simple. Linear term is the duration, quadratic term is the convexity, and so on, right? That's why you see why it's important for these guys to define duration as the negative, because they want to get rid of this minus sign.
So in this case, the value as a function of the rate is...
Yeah, so if you go back to this one, there's just 1 equal to 1, plus 0 plus 0, yeah. Right? And here it will say 1 minus 1 divided by 1 is equal to 0 plus 0, right? Exactly. Huh? Now this is important to work through, because that's why this guy is just doing the job. You know, it's just you got to work through the examples.
The r that's given.
Yeah, it's just the point around which you do the Taylor series. You could do it around 0. I wouldn't do that. You know, you are at some point, right? And that's this reference rate or the prevailing rate, the one you started off with, or you know, whatever, huh? And then you just move. This is not a time movement, right? This is just an imaginary movement, huh? That you are just looking before you do the investment. You say, I'm going to try to do and get this bond, and the rate is now R. What would happen if the rate were S rather than R, right? You know, this is all imaginary, all in the future, right? Huh? Okay? I'm just saying that to you because you have a tendency to then go back in the time domain, right?
This step is definitely imaginary, but you can combine them. 1 year changes.
Yeah, but that's not what we're doing here. I just want to hammer on that we're in the frequency domain here. All reasoning is in the frequency domain at time 0, right? We could do other things, but that's not what we're doing. That's precisely why I'm repeating this.
That makes it more complicated than where we are. Right?
Maybe, yeah, but maybe less complicated, but yes. If we were in the time domain, we'll be exactly doing that. And I'm going to show after the break how the two will interact, okay? But we're not, we're in the frequency domain. We're standing now, we're thinking of buying this thing. We're thinking of buying it at rate R, right? Huh? Okay, so it's worth this, right? Okay, and we think S minus R is R minus R is 0, okay? We think that's what it's supposed to be. And then we're going to imagine that S is not equal to R, okay? This is not S changing over time, you know? You see, huh? So all frequency domain, all our thinking is in frequencies. You know, it's very important to see this, huh? Okay? I don't want to say it gets more complicated or less complicated. I just say it's different. It's, you all know, eh? There is no time here. The only time are maybe some fixed times, like a delay or something. Okay, all right, but no variables. Okay, so this one is clear, right? So spot payment, you know, it's just cash, present value 1, no risk, duration 0, convexity 0, all risk factors 0, right? Okay, so the risk function is just equal to 0. I like calling it the risk function, I don't know why, right? Interest rate risk function. I don't think they do that, but I kind of like it. It's just something that we are inventing here, this kind of stuff, right? This doesn't really exist. They do the calculations, but I think 2 lectures ago, I talked about the big step that Laplace made, that he started seeing the Laplace transform as a transform, not as a number that you would get when you calculate the integral, right? So that he lets S be a variable that becomes the argument of the number you get. This is the big step. And all I'm doing here is, it is new, but all that new is pushing through this inside of Laplace all the way to start defining these kind of functions, the value function, the risk function, all these functions. And when I say function, I mean function of S, of course, right? So we could plot this stuff on the Riemann sphere. I didn't do that, you know, because on the Riemann sphere it will be a single point, and you will see immediately that the Taylor series has no derivatives, right? Okay. All right. But it's harder to take derivatives. I first prepared this lecture thinking I'll take derivatives on the Riemann sphere and you can do it, but then I thought, come on, huh? This is just gonna distract from my basic message here. All right, so now I'll do a deferred payment. This is called 0, but what I mean here is jargon for a 0 coupon bond. So what's the cash flow on a 0 coupon bond? Well, you get absolutely nothing until moment tau, and where you get your payment, your principal back, right? Okay, so no dividends. No dividends, no coupons, I mean, right? So, boom, okay? So, that's the cash flow, right? So it's an impulse at tau. So when t is tau, this thing becomes 0, boom. What's the present value? Well, we calculated that. That is the exponential e to the minus tau s, right? Why? Because all you need to do is bring this thing to the present, and then you have v of s, right? But notice that this is not a function of tau, right? Tau is just fixed. That's the maturity. That's when this payment comes, not a variable, right? Okay? Otherwise, this whole analysis is invalid. There's only one time, and that's t. Tau is not time. All right? So this is the value, and it's just this one number. Tau is known, and it varies with s. Okay? That's what I mean by function of s. All right? Now, this is a function, and here it is. If and I plotted this right because I just had take z do this. I was going to say if I plotted it right, but I think I did. So what's a Taylor series, right? Now, that's not that hard to do because you know that the v of r, that's just you plug in r for s, right? And then you have to, the derivative, you bring down a tau, right? Because you got to take the derivative with respect to s. So you bring down a minus tau, and then you plug in r, right? Because we're evaluating everything at r, okay? And then you multiply s minus 1, and that's what you do for here too. You bring down another tau, minus tau, so you get a plus sign, and blah, 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 right? Now, here you go. Then you can calculate your risk function, and here it is. All right? Now, this is a famous result. Okay, it doesn't look like it, because what does it say? It says the duration here is exactly this moment you get your payment. All right? So this is sometimes called the maturity of it. So if you buy a bond, it has a maturity the moment you get your money back. That's when it matures. For an option, they'll call it an expiration, but it's all the same stuff, right? Okay. Yeah. But so this is the idea that was behind duration, that somehow for other bonds like the ones we had, this is also a bond, there's nothing wrong with this, it should generalize this thing, right? Now here, of course, it does, because you will just say tau is 0, right? Huh? But here, now you'll see this is the, but now for more complicated things, what is this tau going to be? All right? That's interesting. Now, what's also interesting is to see that this thing has convexity, okay? So the thing is moving around. It's somewhat surprising, because you wouldn't think that, and but it has infinite many other terms. So I'd be curious to see what the consequences of this are, but whatever. So this is just not, you still have to worry about such a bond. It still has convexity, and we all know that when you get closer to the maturity, funny things start happening, it's still a complicated instrument. This is the point. The exponential is still, it's got a lot of terms in its Taylor series, okay, right? It's easy from a Fourier perspective or Laplace perspective, but it's not easy from a Taylor series perspective, because when you just know what happens in a little interval, you will think you have a straight line, but you don't. The thing keeps changing, okay? And the change keeps changing, and the change of the change keeps changing. So it's still a rather difficult thing alone, even if you don't get interest payments, So there's quite a bit of risk. Of course, this subtracts from the risk, this one adds, this will subtract. So they'll start alternating, because every time you bring down a -1 here, okay? All right.
We had the, probably didn't actually call it, but curve, but graph you showed for all S's. So
here, this will be the duration, right? And then this will be the convex. If this is a quadratic function,
Exactly, and if you only take the first two terms, then approximate it. But
a little bit better than that, but it's not, you're never going to approximate it with a finite Taylor series.
And the part that I'm missing now is the
okay.
The talk about, but 1 divided by 2.
Yeah, factorial. Yeah. So a deferred payment is a risky, is a complicated thing to assess the risk of, and obviously if these steps are really small, this is going to be small. But if this thing is humongous, then this thing will start blowing up. Of course, if this is really small, then it's going to be okay. Then it starts getting smaller. So. It's a lot of exploring to do. And this is something everybody does all the time, right? Can I borrow some money from you? Yeah, sure. When I can pay me back, like, or whatever. All right? And of course, it has to do with the compounding, right? So if in the period you borrowed it, you start infinitely compounding that money, you can go, and the rates go up and down, you can make a ton of money by a simple loan, right? Which is what people do. If you're compounding at a higher frequency than somebody else, this is what the bank probably does, and there's just a lot of money you can pull out of compounding. Okay? This is how they figured out infinite compounding, actually. Just the banks trying to make more money. So they would compound infinitely when they loaned you money, and then they would compound, yearly or something when they borrowed money. And then the government in the States forced them not to list interest rates anymore, but effective yields. So given the compounding frequency, how much are you effectively getting? Don't give me the interest rate anymore, okay? So if you go to a bank in America right now, they're 0 anyway, but And remember, there'll be the interest rates, and they will be forced to put what they call the yields, okay? And then they would make the difference between an interest rate and a yield. So it was a made-up word to say, well, what is this effectively are you getting per year, okay? There's the customer. It was just a clever way to gyp the customers, and the accountants had kind of figured it out, but not through this formula, by the way. They're just seeing that if you increase the compounding frequency, you can make money. I know guys who do it, actually. They make the deals, and then they put in some very small, I'm going to compound it, this thing, and then the deal is all of a sudden a lot worse. Huh? Okay? So very satisfying this all shows up in our risk function. You just got more risk then, or less, right? Okay? Let's look at a perpetuity. A little cramped together because the way LaTeX does it. So you have your constant cash flow, so remember what that is, right? So and we all know that the Laplace transform is 1 over S, all right? 1 over the discount rate. If you don't know that, you can go and watch the last week's lecture. And here's the Taylor series. I did this myself. That doesn't bode much well for its correctness, but I think it's correct. The other one I did myself too. So obviously at R, it's that, right? I take a derivative of 1 over S. I got minus 1 over S squared. That's right, no? Huh? Yeah, so that's right, times this. So I think it's right. Huh? You got another minus sign coming down, everything plus. Huh? Okay.
Now you missed it.
You're right. So I didn't do it right. Yeah, so I have to do the 2 here. I want for factor 2. But you get the message. Huh? Now that's also interesting, right? So now this one I can, of course, deal with. This one is easy, right? But you see the lower the interest rate are, the bigger this thing is. Well, of course, right? Because if interest rates are really low, say 0, this thing is humongous, and a little change in interest rates is going to whip up the value, right?
0 to 1% is way bigger than 10 to.
Yeah, that's what this is saying, right? So this is, if R is very close to 0, it cannot be 0 because this thing will blow up in your face, right? Or, but this is the case we have now. So you can see the maturity for small changes in S, the duration are going to be humongous, you know. So the stock market is quite unstable now, you know. So a very small rumor that the ECB or the Fed is going to do something is going to whip these things all over the place, you know. So the Taylor series, the present value, will move very, very fast, all right? Okay? Not so much the first term, that's still going to be okay, but look at all these guys. I mean, huh? They just get smaller and smaller and smaller. I mean, you have enormous convexity, you know? So it starts getting bad, and then it starts getting worse, and the whole thing, that's what you call a credit crisis, right? Huh? The values are just plummeting.
As long as the change is smaller than the interest rate, then you can cancel them out and
right, yeah, sure, as long, right? But now suppose, like, I think it was a year ago, maybe even 2 years ago now, is that all of a sudden, in the beginning of the Corona time, you saw the market was tanking. And everybody thought it was due to Corona, but that was not the case. What was going on was the oil price was dropping really low because of a price war between Russia and Iran. And this was causing those frackers to all go bankrupt because they can't sell oil when it's below $50. Now, these frackers, they're all financed with bonds because, you know, interest rates are low, so why would you issue stock, you know? So these bonds all of a sudden, you know, were becoming pretty worthless because there was a huge credit risk all of a sudden because these guys are making no money. They're bleeding money. So interest rates on these bonds were going up like crazy, okay? So the yields on those bonds had to go up. But they were pulling other bonds with them. Okay, that's what typically happens. So the interest rate at which all bonds started being discounted started going up. So because they were so low, the stock market started tanking like there's no tomorrow. And then I remember Trump, he had to go and call Putin and tell everybody to lay it off. And then the oil price you saw, and he started buying in the strategic reserve. You saw the oil price restabilizing. You saw them getting it just about 50 again. And then the interest rates went down again and the stock market stabilized, okay? And then it took off again. But that was the real problem. Now, they have a similar problem now, okay? That as soon as something is going to come and jack up interest rates, you know, what do you think is going to happen to your house? I mean, it's just, you know, if your income doesn't change accordingly, you know, the income doesn't grow with the same amount, and your income is not leveraged, so that's not going to happen, right? Huh? So you can see this happening, okay? You can see this happening. And of course, this is a little bit worse because a bond will have this, but they will have bonds that are way out. But somehow here they even have this principal repayment, so you can add the effect of the exponential function on it, right? Because you also have to add the Taylor series of this thing, which is that exponential, right? So it gets complicated, right? But you can see the power of this thing. All these stock market movements, you know, now basically everybody knows it's about interest rates, but this thing is just telling you explicitly, all right? Okay. Now, for bonds, of course, you don't know what this S is going to be, so you have a probability distribution over it. It will change things a little bit. But, you know, now, huh? But you can, once you have this, you can put a distribution on there and then calculate what this is just a function on, you know, so you can calculate the distribution of your losses and you can do all these things, okay? That's called a value at risk analysis, okay? So the point here is the Laplace transform. I don't know if I did another one. Oh yeah, here. So let's go to the applications. So the Laplace transform is if you look at the Taylor series expansion, it's just it's a very effective device of modeling interest rate risk, much more than the hodgepodge of stuff they would use. Okay, so I just named a couple of things that I could think of, you know. So. And it all goes under this topic of immunization, okay? So what do they mean by that? That doesn't mean that you have COVID and that they're going to make you immune to the bacteria. What it means is that you'll have a portfolio or you have some kind of project or something, and what you're trying to do is make it not so subject to changes in the interest rates, okay? So otherwise, your whole project can stand or fall depending on what the interest rates are doing. You don't want that. You want your business to keep going. You know, that's what the bank wants. That's what these frackers really want, right? So they never worried too much about being too immunized. They were not immunized at all. They had enormous amount of interest rate risk, you know. Yeah, because they all have bonds outstanding. Had they been capitalized, it doesn't matter. Right? So the thing is, if you're capitalized with it differently, you just have stock. So you issue stock, then you have your own money, you know, so the investors take up any losses or gains or whatever. So you won't be able to, you won't go bankrupt so quickly because you don't have to pay dividends. You pay dividends, you just stop paying dividends. That's what Shell does, you know. So they're well capitalized, we say. You know, they don't have many liabilities other than the shares, okay? So either way, you look at some portfolio, so you try to immunize yourself. So you want the total value of this portfolio, or whatever it is you're looking at, to stay constant so that these derivatives, you know, don't kick in, huh? All right? And you prefer if you do a duration analysis, you don't want too much convexity and other things, okay? So what a lot of guys do is they make these bonds really complicated. They put in options and riders and this, and you will see that the duration is just fine. But these things, they all kick in the higher derivatives. So the customer is screwed anyway, you know, but then through the higher derivatives, okay? They have a call option in there, but they can call it, not you. So blah, and this. So you'll see for a big change in interest rates, they can just say, we give you your money back. But a big drop in interest rates, you can just not say, well, hey, I want my, I want to loan you more money or something, right? Huh? So you'll see that they get very complicated, and the reason is all to obfuscate, to make you believe that your duration is okay, because a Bloomberg terminal or something will just tell you what the duration is. Maybe the convexity, right? Huh? You know, but then they peter out. Huh? An option will kick in much later, because they won't go in until the change is bigger than that, some hurdle or something. If the change is bigger than that, then we will, you'll know. So they immunize themselves with all these things, okay? So either way, they try to get this thing to be constant, and they draw the contract like that, making you believe, you know, that you are being very well paid for the risk you're taking using the interest, you know, or the premium that you get on the final payment. And in fact, you're being gypped, okay? Now, I believe that you as a economic engineer, you can do better than these finance guys in calculating that. They don't know what the Laplace transform is, but they're not stupid people. And usually the stupid ones, they die anyway. So you know, I don't mean die real, but financially, you know. So the clever ones who have something that seems to work, who get the price right, they make the money, and they dominate the market, you know. And once in a while, somebody clever comes along that out-clevers them and then takes their money, and then they hate it, and then they try to shut you down, and you know, that's how we make money at this business. Not by betting on the future, but trying to be more clever about the guys who think they're clever, okay? Okay? So that's used for portfolio hedging, right? So in the portfolio hedging, you may have N securities in your portfolio, and the total value is just the sum of the values, you know, because the total cash flow is the sum of the cash flow. We take the Laplace transform, presto, right? You know, it's a vector transform. It's a linear transform, so you can just keep the plus sign. And then you just look at this total value, and you try to look at, you know, the Taylor series expansion, right, for changes in the rate. Then you can do what Brit is doing. You basically have two cash flows, one for your liabilities. These are the depositors at the bank, all right? The other one is on your assets. These are the lenders of the bank, huh? They're loaning from the bank, right? And then what is the bank getting in? Is the cash flow is the difference between the two, huh? That's their profit. And you take the Laplace transform, and you'll get the profit or loss, right, in terms of the value of that profit. And then you can look at the Taylor series and the loss function, the risk function, and see exactly where the problems are, okay? They got big problems now, I think. So if there's a big change in interest rates, you will see that there's some terms way down there that may kick in, and the bank may be bankrupt, you know. Of course, that's exactly what happened in the credit crisis. I mean, there's a big change in, due to the credit crisis. It starts in the housing market. It seeped out to other things. The banks got into trouble. They didn't have enough cash to pay their obligations, and it was all about, you know, a bigger change in discount rate than anybody ever expected. Okay. There's another thing called the value at risk, and this is a very popular. And then they look at possible losses, and they'll have some kind of a probability distribution function over the losses. So this will be value of the total, and it will be around something, and these will be your losses, and you'll be gains, right? So this is the value of the total value, right? And you don't know what it may be because there is a probability distribution over what these possible S's could be. All right? And that's what this probability, this is a PDF, so this is the F of V. And so, and then this probability is F of V dV, Okay? And then what they'll look at a 95% tail, and what's the probability of losing more than some amount of, this is where you are currently, say V at R, you know, And it's called a value at risk analysis. A huge field, books and books are published on this. But what would you do as an economic engineer? Well, I would just go back to my definition of this function, but now I have a PDF, a probability density function over this S. This R is just a number, right? Because I don't know what it is, but I have some idea where it might move. So I'm saying, and there are, you know, and it might move here up, and it might move so much down. Now, if you're at zero and you say you can't go float on zero, this is not true, you could. You would have to imagine that it's something like, you know, a little strange, you know, like that, But whatever. But if you have a PDF over here, you can always calculate what the PDF is over this or over that. Not over that, over that, And you use that PDF to calculate this. And now this value at risk, so this is this delta V at which you have some, and this is your 95% quantile or something like that, okay? Now the list goes on of stuff that you could do with this. Now these are just some ideas for people that can use this as far as interest rate risk. I see. I think we have naturally come to the end of the first part, so we'll take a short break, 10 minutes, and then talk about transfer functions and returns and liquidity. Okay? Okay, now for the second part of today's lecture. First of all, any... Oh.
Daar. Goed zo.
Okay, very good. Now we can really get started. And despite my loud voice, I'm sure that with a muted microphone, it still doesn't work. Let's get going on the second part of the lecture. But first of all, any questions about the this idea of risk and duration and convexity? Any remarks that you may have come up during the break? Nope.
Okay, I have to remark that in the book of John Hill, they do, how do you say that? The derivation with the Taylor expansion of the convexity and the duration.
Interesting.
The same way you explained.
So he does a Taylor series expansion of some function. And how does he call that function?
I have to look into it.
Yeah, maybe you don't...
Yeah, just function f of x.
Some function, whatever.
Yeah.
Yeah, so he has this idea, but I think what you should do probably, and there's probably the lecture is not the right time to do this, is take a look at what he's trying to do there, because he's got a couple of problems. First of all, what is this f of x? What is x? I mean, you can say, okay, x is that rate, but what's this f? How did he get there? Did he just posit it? I mean, one thing you should keep in mind, and this is also going to be the topic from now going on, is that these Laplace transforms for us don't come from nowhere. I mean, we just have, from our time domain models, whether it's a bond graph or whatever type of models, we really have functions of which we can take the Laplace transform, you know. I'm sure John Hull, he's got an excellent book, does not have that, right? He must imagine some function and that otherwise is not imagined by the day traders, and then try to explain it as a Taylor series. So that's interesting. I'd like to see more of how, you know, what terms he uses, okay? I somehow omitted to look at his book, you know. So, yeah, thank you, Britt. Anyway, anybody else a question about this? Then I'm going to proceed to the next parts of the lecture. And the first part was about risk, and the second part is going to be about return, and what is a return, okay? Now, the short of it is that the way I like to see a return is as a transfer function, on par with something that I'd like to call the yield, and I'd like to call the liquidity. There's not one name for a transfer function, and neither is there in engineering. Some are called an impedance, some are called reactance, some have no names whatsoever.
It depends on what the input and output is. You have a voltage or a current to voltage, or the other way around, you're talking about impedance.
Right.
And the other way, if it's the other way around, you're talking about
exactly.
So it really depends on what the units of the signals are.
Right, but if they go from a FR to an FR, or from a voltage to a voltage, they have no name.
Yeah, and then they're...
Yeah. So the only one they have is when they go from a force, so voltage, to a quantity, or inversely, right?
And you go to a conjugate.
Right, exactly. So this idea of liquidity was originally where the transfer function was based on. And then later this was generalized to go from one signal to any other signal in controls. But they took that idea that I wrote at the bottom here, and that we will be talking about liquidity and then illiquidity. Okay? But what we've been doing up to now is kind of focusing on this effort alone, or economic force, or want. And for it, we took the rotational analog, in which case it is a cash flow, the want, right? Or at least has units of cash flow, is what you would call the cash flow. It's the future cash flow in that sense, not the accounting sense, but the investment sense of it, okay? So it's a torque. So that's how we've been looking at, and we're looking about how the Laplace transform of one torque relates to that of another torque, okay? So the Laplace transform of a torque, which is a cash flow, is indeed measured in some currency units. And here's just another one, right? It's also measured in some currency unit, right? So if there is a relationship between them, then that would be measured in nothing, in percentages, okay? And what do I mean by relationship? The idea of the transfer function, and this is also an idea that gets bandied around over there, is that this is somehow some input that you have. So say an investment you're making, or some capital contributions, you know, to your project. And then this is the project, all kinds of stuff happens, you don't know what, right? And out comes this thing, right? This is what is your return, right? This gets returned to you, right? Okay? So this is the value you will get in return for your investment, right? Now, what you can do is say to yourself, well, Okay, if this is the return and this is the investment, then what is the return on this investment, right? Now, all that is really is this is the return. Why do I have a, oh yeah, on this investment, S, right? I mean, that's literally what this says. So maybe I'll write this. This is the value of the investment divided by, no, the value of the return divided by the value of the investment. This is literally what this thing is. Okay? Now, if I call this H, and it's a function of S, because everything is a function of S, then it's obviously true that if this, the input, is your investment, or and the return is what you're getting out, then this thing is the ROI, return on investment. But usually we just say return, okay? So, and that will be measured just, it will be unitless in this case, okay? So the return is like a transfer function. It gives you some inflow which you put in, then it goes, right? And out comes this, this value that gets returned, you know? So the word return, even if you look it up on Wikipedia, they'll admit it kind of gets used in these two senses. This is the part of the return, and this is also the return, right? But sometimes they'll call this the return on what, and then they'll specify what the input signal is. But you could have the return on something else. I don't know, capital. And these are your capital contributions, okay? All right? So it's just a way of looking how one might reason about these values and how they are related. Up to now, we just had V1 and V2 or V in or V out, but there's a relationship, you know, if it's only that the one is the other divided by the one, right? Now the one, the other is the whatever. I mean, this is a simple relationship that's always true, okay? There could be other relationships, but this is the one that we're aiming towards, okay? And this is the one inherent in this type of reasoning, okay? All right? So that's the next step we're going to make, is rather than seeing these values, you know, these Laplace transforms, just like this is the Laplace transform of that, and that's for that, and we can aggregate them by summing them, boom, we have something of that. No, we're gonna have a more of an input-output, not causal, but input-output thing. How do I get from one value to another value? I throw it in some machine, and effectively what the machine does is divide by the stuff that I have going in and multiply by the stuff that I've coming out, and then spits out what I get. So how do I get from one V to another V? That's basically what you're doing. And you want to map that into multiplication because it's so easy. And then so you can add present values, but you can also multiply them. And if you can do that, you have what's called an algebra, right? You can do algebra when you can both add and multiply. So numbers are an algebra. You can add numbers and you can multiply. The complex numbers are an algebra. Vectors are not an algebra. You can't really multiply two vectors. You can take an inner product, but you won't get another vector. You get a real number, right? You can use the outer product. You'll get a third vector, but it's in a different direction. You can't really do it, okay? You won't get another vector that's in the plane of the two vectors that you have, okay? But numbers you can, complex numbers you can, quaternions you can, there's a couple of stuff you can. And the other thing you can is transfer functions, okay? You can add them and multiply them. And if you make these block diagrams, they're just a representation of the algebra of transfer functions, okay? So you'll see a block diagram, and here'll be a summer. So then here'll be some other block, and then, I don't know, maybe they feed this back, and then here another block, and here a block. So these ones are multiplied, and here you specify how you add them, right? So the entire algebra of these transfer functions or values can be represented now in the block diagram case, okay? So we'll figure out under what conditions we can multiply values and what we can add them. Now this is the step that's not made in economics. You can add value, sure enough, but multiplying, I've never seen somebody do that, except in very special cases, you know, when they have a cash payment and then they multiply it with it. So instead of a coupon of $1, you get a coupon of $5 or something. You know, very simple transfer functions, okay? But not in a systematic way. So this is, for a controls guys, this is like, if you look at any article on what control is, this is probably the first thing they kind of show you, is this block diagram. That's what we do all the time. You know, multiply and add. Actually, we don't do much more. And I remember Ruben sitting here and asking him what the Laplace transform was all about. And he says, well, it just makes everything easy. I don't have to do differential equations. And he told us, yeah, I can just multiply, you know, and add. And then that's it. Because we're engineers, we don't want to solve differential equations. We don't want to do this. We just want to multiply and add. So the whole reason for us, and basically the multiplying was the important part, because you want to multiply by s or divide by s, you know, with your integrator, right? The multiplying was the important part because it takes care of your differentiation, which you hate, you know, and other things. Okay, so let me just skip for a second to the other slide I have here, just to tell you what's going on, and then I'll finish my first slide here. So, you know, forget about this for 1 second. Here I have the time domain, and we would call this the frequency domain. And in the frequency domain, we can add signals, okay, just like we can in the time domain. But when we multiply them, you can't really multiply signals. You have to convolve them. You have to do a convolution. So if you work through your block, you're sitting there with this convolution, and you hate it. You know, nobody really figures out what you're doing. So the whole trick of this Laplace transform is to go to this frequency domain and maintain this business of adding. You still want to add these signals because your adder has to work both in the time domain. But the blocks that you have, they just have to be simple multiplication. Okay? That's the trick. And that's the one property of the Laplace transform that I didn't treat. And I want to treat it now. I'm going to treat it in the context of this economics application, and just show you how that it's really quite something trivial, you know? I remember last semester I had something about a smoke function and this and that, and people thought it illuminated, but the problem with it was about smoke, and this is not a course on smoke, okay? Now before I proceed, let's go back here. So up to now, we've just been dealing with this kind of situation. I like to call this a return, okay? But you can call it whatever you want. Sometimes it's not a return, it's, I don't know. Huh? And then what do I do when I have a quantity? So this is the Laplace transform of some kind of flow, some kind of velocity, right? Huh? And I go to some other quantity. So maybe I'm Ozai, and I have a plant, and I have all these inputs, and by inputs I don't mean capital and labor, I mean all these raw materials that are going in, and some other raw materials that are going out, you know? And maybe I measure them in the same thing, so I have crop yield, so I have seeds going in, and then seeds coming out afterwards when my crop, you know, when I can do my... when I get my harvest, when I can harvest them, okay? So then you will have some seeds going in your ground, some seeds going out, and then we would talk about the yield, okay? This is just a traditional word. And now we call that the crop yield. And I believe in bonds, they started talking about yields only because they needed a term to describe what investors were really getting, you know, accounting for the continuous compounding. And they just took this name because it felt real, because it was about crop yields. But really, yields are a physical thing that belong to the returns, which are the financial thing, okay, in the English language in any case, okay? Now, that doesn't mean that I say don't use yield for bonds, or in that sense. It just means that as a sort of general terminology, you know, independent of the specific application, whether it's real estate or this, it's good to keep these things distinct in this way. All right? And then finally, we get something that is quite interesting, is what if you put a cash flow in and out comes some kind of, you know, some quantities, right? Huh? Some stuff. That's interesting, you know. So you got your farm and it's threw in all this money and out comes all this, you know, this milk or I don't know what, right? Huh? And then you'll get something that is, yeah, in units per dollar, right? Okay, in items per dollar. And this has a feeling of what is it? The inverse of impedance, that's admittance, you know? Right? So you put a voltage on something and out comes this current, okay? So why do I call this the liquidity? Well, the liquidity is just saying, like, suppose I throw a lot of stuff in the market. I mean, how much is it going to change the price? So for every change of price, how much is this going to change, okay? And you'll see that this measures the admittance is how liquid, how easily the current flows through the circuit, okay? I call this the bid and not the offer, because what happens is, logically speaking, maybe I'm bidding for something and then this whole thing happens, and then the system on the other side, maybe I have this big system here and here is a port, you know, electrical system, and I'm bidding here with my voltage, and out comes this current here now, which is offering me this current for my voltage bid, you know, now. It's one way of using bid and offer. Offer would then be about the physical goods, and the bid would be, you know, you could turn it around, you can ask and, you know, now, and you can do this, okay? This is some terminology and some ways of looking at it. No, you know, so these are just the kind of three basic transfer functions. So if we're okay with this, I will now just keep, I will keep my focus on this first one, you know, but obviously we can extend it, okay? Now, so here you see what I'm trying to do. So we already looked at portfolio composition. That was in one of the applications of the end of the first part of this lecture, when we say, all right, we have a portfolio of various stocks or whatever may be in there, and we look at its Laplace transform, and it's the sum of the Laplace transform of the individual securities, or you can look at houses, you can look at anything you want, okay? Now what we want to do is, what happens if, okay, I buy this house. Now, how do I buy this? Or buy this security, or buy this. How do I do this? Well, the obvious one way to do that is just to take a lump sum, give it, boom, and you get the stream, right? So you exchange an impulse for something complicated, right? That or something complicated. That's what usually goes on, right? Now, if you do that, you can pretty much figure out what happens. So your capital contribution is just this, right? So you contribute this amount of capital to your project. You can calculate the IRR. You can calculate all of this. But very often, these contributions are made in installments. Like you may have a contribution here, then another here, then another here. And in general, you can like stuck this in and see what you get out, right? Now, this is a more complicated problem, obviously, because what you're going to get out will obviously depend on what happened here in the beginning, like that's your initial payment. But then at a certain point, you start compounding the effects, adding effects, because now you're making another payment, say here, and that's going to affect this thing in various ways. But the effect of the first capital infection is still going on. Then you have to add the effect of that one, effect of that one, and then you add them all up. And here, you're going to have to look back at what all the initial contributions were and add up all the effects. You see that? So at any point in time, you got to see what the cause was, what the original of this thing happened, and then figure out what, at your point in time, now, all the consequences of these things were and add all those up. So you got to go back in time, collect all this stuff, add them up, and then there you have it, okay? Now that's not multiplying. That's not multiplying. Obviously not. I'm not taking two signals, F and H, and multiplying them. No, this is something else. Let's just say it's something really complicated. This is complicated multiplying. It's this, right? And this thing is so convolved that we call it a convolution. All right? Now what we want is that's fine, that's this thing, but what we want to see is that in the discount domain, this becomes just simple multiplication. Right? So all the effect of all those weird things all together, now put into a Laplace transform of your input, the value of whatever you do. If you multiply that out with this transfer function, whether it's the return or the liquidity or whatever it is, should give you your actual return or your actual stuff, all right? That's the trick, right? So in the time domain, this is hopeless. But in the frequency domain, it is certainly not, okay? And we know what the outcome is, that this is going to work, right? And now we see the real value of looking at values rather than at cash flows, okay? And why? I mean, for the finance guy, they can be forgiven not to have noticed this because for them, this is a triviality. I mean, that's kind of how I presented it. You just say, this is what I want, this is what I have, or I'm doing something magic in between, right? But you guys are different. You spent the whole first semester learning how to make these models, right? So this guy's got a bond graph model doing A, some oil. This guy's got something with that, and he can just take a Laplace transform, and then from any one signal he can go to another, but he just knows what it is, right? And he can just multiply. He can even do it in his head, He can do controls now. He can do this. He can add another box here, feedback what he's thinking, seeing how this goes wrong, and seeing that he can make this, whatever it is, get going, okay? Why? Because he can just multiply this out, right? And then, with a simple bit of algebra, you all know that the closed loop is going to be, control 1 divided by 1 plus control, whatever, okay? That's the point. All right? Now, you all see how this is going to work out, but let's just go through a specific example to make this really concrete, okay? So you see that the magic you do is really not magic, okay? Now, I drew this up as an example, and I'm really bad at examples, so I bet you I got all kinds of issues in here, but the idea is going to be good, okay? It's going to be there. It's not going to be. I want you to get the idea when this is a. So what I try to do here is create a very simple system. So a very simple way to relate an investment to a return or something, okay? Now all I have is what we call a forced order system, and here it is. You got a spring and a damper in series, okay? And what is this? This is some storage, right? And this is just some cost of carry of this storage, all right? Here's the bond graph, and I'm pushing on it here, all right? With some force. And I want to see what this force is. I believe I did this right, okay? So this is...
supposed to be a zero junction in the bond graph? I'm just wondering.
The way I did it, I just looked at this loop here, I, right? Huh? So I just looked at the velocity of this point, I think. So that I called the one junction, and then...
Current cannot go anywhere else.
yeah. So you should, but I was able to collapse it like that, right?
Oh, you cannot do a zero junction with a C and an aperture.
No, but you could imagine a zero junction here with a C on it and then collapse the thing, right? Huh?
See,
You see? Huh? But I mean, but this is correct, right? But you can also see, I just look at what is the velocity here. I just took this thing because that's where I happen to want to see the force, and then, you know, now, which is the current going through whatever, right? You know. But that's it's a good question because I always ask I first put a zero junction in there too. I go like, come on, you can't do that, right? I think this is right. Huh?
Yeah, because the velocity is a multiple. That's what movement.
But this is not right.
Because for the velocity.
This should be like this, yeah.
There's a different.
Yeah,
Exactly.
thank you. I think this.
Was referring to.
Yeah, so now there's a different force on the damper spring.
Yeah.
Just like the capacitor and the.
Yeah, the problem is here the velocities are the.
Yeah, they are now splitting the forces and sharing this.
Yeah.
Sharing the.
I want to split the voltages, right?
Yeah.
Huh? Yeah, that's what I'm doing in the network. I mean, this is a force splitter, right? So part of the force goes through here, and part of it goes through. Yeah, that's where my mistake was. Yes. Interesting. I copied this from the example. I just looked at it, and then I just wrote it down. I did it out of my own head from my own textbook, graduate textbook on controls from MIT. And they must have made this mistake. I saw more mistakes in there, but huh? But it's wrong. Thank you.
Well,
huh?
it's not wrong in itself, but
Yeah.
the analog.
No, that's not the analog. Yeah, but the system is right. Huh? And I think this is the right transfer function.
No.
No?
No, it's. I could. Not sure.
All right. You know.
Probably.
Yeah. You know what? I mean, this is. I want you to just go along with this story, you know, and let's leave the details out. But
at our defenses as well.
huh? No, no, don't do that. But you only have one defense, and I have all these lectures. And I realized I had some issues here. But what I want to do is more illustrate the results. So this may be right. I think I got this right, but who knows? Okay? Huh? Who knows? All right, so just you have a system, and this system, and it has its own analogs, and there's only two things going on, storage and the cost of carry, okay? Jump. Huh? And I can look at the relationship between these ones here. So would I want to do that? Well, I'm interested in the convenience or something as huh? Somebody is demanding this stuff, whatever, huh? Okay? So let's do it in the time domain first, okay? And even this might be wrong, but you'll get the point, okay? What I'm trying to do. So in the time domain, this block looks a little different. I have here a time function. I'll just use a little h for that. I have this cash flow coming in, and I have this cash flow coming out. So these are my investments, and these are my returns, okay? And this is my time domain magic, all right? This is just my bond graph or my differential equation. So what can I do? Well, I can just make a single payment, and I get this out, right? Or I can look at the impulse response of that system. It's all the same, okay? And what you get in the time domain, I believe, this is right. This is this exponential decay. Otherwise, it's something like this, but think this is right. It has to be, because you put in something and that thing is going to decay towards whatever you choose as a 0. Huh? Okay? So that's easy enough, right? So what you will say in the time domain is just, look, what's my problem? And this is what these economists will say. I make this investment and my IRR is what? Well, I think if I calculate it, it's e to the minus k over bt, something like that, right? Huh? Right?
So in a case,
These should be inverted, right?
or normally you do S plus B.
Yes, exactly. Very sloppy, very sloppy. Don't do this on your final, but this is to show you how not to give presentations on your final. But thank you. Right? So this will decay, I think, like this, right? So this is the decay rate. Now, what was I going to say? Yeah, so what's the problem, you might say? You know? So this is just, these are my returns. Why do I need anything? This is what they do, right? Because they always look at a single payment, right? So what's the internal rate of return on this thing? Is exactly this, right? K over B. And that's what they'll say. Then you will read on an article on the internal rate of return. What are some of the problems? They say, well, this. But the biggest problem is, what if somebody makes another payment here, then takes out some dividends, then puts this, then the whole thing goes pear-shaped. You know, nobody knows what to do anymore, because how are you going to solve this problem? You know, and you can read as many articles as you want, and they all will give this as a limitation of the internal rate of return and discounted value approach. Okay?
Where we're looking at right now, I buy a car and the car depreciates, so the value.
For instance, yeah. Right.
And now I repair it 2 times, sell 1 wheel, and then.
All right, I have an investment and I start buying stocks. And I have a portfolio, and I buy some more, and then I buy some more, and then I sell some, and I take, whatever, right? It's called capital contributions and capital distributions, you know? So you contribute capital, you can have a company, you throw all the capital in, let the company run, or you can say, well, I'm going to contribute more capital, right? I'm going to, just do a illicit for shares, a tender offer or something, right? Whatever you want. These things happen, and you can't use the concept of internal rate of return at that point. I ran an investment fund, and it was a major problem. I mean, investors would want the internal rate of return, and then we were always inserting new in this, and we had to report that we couldn't get it, and they would never understand why not. Okay, but you can't. I mean, you can do as if, but you can't. And one investor who insisted, we finally had to, I don't know what we had to do, get rid of this guy, but anyway. So let's look at installment payments. So you do all these different capital contributions. So here I have one. I just plot them like this now, And then obviously, so according to this one, this cannot be like this. This has to go something like that, I think, So it picks up a little thing. Yeah, so I do this for a small period, but there's a reason. There's a rhyme, there's a method to the madness here. So here comes another one, and then boink, you see another exponential coming in. And here's another one, there's another one coming in. So how would this total return look according to these three? Well, this will be fine. So you get here, then you have to add this part, right? So something like here. Then they will start decaying at some, I don't know, some other rate. I don't really know how it goes. So you get here, then it will get another boost, and then, So you have to add them all, right? I didn't even do this, right? Now you can imagine that if I do something like this, you're gonna get, I don't know, Something like that, right? Huh? Okay. Now, what does this adding mean? What do I do? Well, I run over here, and I know I'm just going along here until that point. So I have to add up. I have to look at the contribution of this thing all the way up to tau equal to this value over here. All right, this is the first one. Then when I hit that value of tau, I got to add a big point to it, right? And then I run further, and I hit another critical point, and I add another big one, right? Huh? Okay, so I got to kind of, at every point in time, I got to kind of look back. I'm integrating this, right? So these are the payments F, I, tau, D, tau, right? Huh? You see? So this is the D, tau part.
Oh, now we really have the curve and not the...
Yeah, but even for this, it will work. You know, I just call this D, tau, right? Huh? You see? This, it just works. You just get 0 here. But you still have to, at any point, first start looking back over tau, you know, back to 0, see what's going on, and then add it all up, right? This is the cause, and this is the way it gets transferred over. I mean, the other one is not coming until sometime later, okay? Okay? Simple. Anyway, it kind of sucks to do this, right? This is not simple multiplying. This is this complicated integral. And we denote this integral by a convolution, okay? And now you see, in the frequency domain, this is trivial, right? You just take this h of t, take its Laplace transform, h of s. I just take the Laplace transform of that, and I can do what I have over there, okay? Or just use multiplication. That's the idea, all right? So the impulse response, that's a single payment for this investment. It's easy enough, sure. But the way we view a general response is the sum of all these other investments, but they're deferred payments. They're things that are going to come a little later, okay? And we add all those up, right? Huh? Fortunately, deferral goes with an exponential, so you see that if you work this out, it will just be all simple multiplication, right? Okay. Now, I don't want to do that, you know, because this is in any text on controls, and they work through it, and they'll show you that these integrals, if you take the Laplace transform of those and plug them in, it will just be called a multiplication. And sure enough, right, you can do the Laplace transform of this, and the Laplace transform of that times, you know, I don't know, Laplace transform of this, you just fill in that e to the whatever, you'll see everything works out, okay? All right? That's key. But you see also how this is really useful in economics to look at this business of capital contributions or distributions, or, well, you know, an investment plan, not a single investment, but an entire plan. First, I'm going to contribute this, you know, like a saver may do, or an investor. He invests a little bit of his salary, then he has to take out later in his life, you know. So he has a whole schedule of payments that he wants to make. Okay, so these planners, financial planners, they try to somehow guess what the stock market would do and what this guy's risk is and stuff. They do an awful job. You can see how with the Laplace transform and our simple transfer functions, it all becomes problems, very elementary problems in control. Okay. It's a huge opportunity for the economic engineer, I feel. And Again, it's not the magic of what makes this work. It's, on the one hand, the economic interpretation, but on the other hand, what's the most important, I feel, is the fact that you guys got this, okay? This you derive from first principles. This comes from your bond graph model or whatever it is, okay? You gotta have a model. Otherwise you have no, you can calculate Laplace transforms of signals, but they won't relate other than in trivial ways that you'll have to make up. Don't do that. Make a model, right? Then figure out how these things are related so you can have some hideously complicated bond graph model with all kinds of things. You pick up an effort here, you pick a flow there, when you start seeing how they're related, you know, when you're done, okay? So you can look at a liquidity or a return or a yield or whatever you feel like. But you start with the model, then you can calculate the value or the quantities of any of the signals that you feel like in your model. They're all flows, right? Or efforts. So you get your values, you get your quantities, and then you just take a Laplace transform of all those derivatives that are in your linear elements. You got I elements and C elements and R elements. You divide by S, multiply by S, or don't do anything with S, okay? And just work your way through, and then you're done, okay? Well, you're not done yet, but you got to just see what your model is. So a bunch of you have nice models, but you have a solution without a problem, really. So what you want to do is take your solution and frame it as a problem, because most of the financial aspects of your system are done in the frequency domain, in the discount domain. Okay, so if you have a model, it's time to Laplace domainize it, okay? And then interpret everything, okay? So I exactly hit 6 o'clock. So with that, I want to end this lecture, and I'll see you all next week, where we're going to continue the discussion of the Laplace transform, because there's way more stuff coming. Okay, we're really going to pick the fruits of our labor of understanding what this thing is for economics, and now we're going to milk it for all it's worth.